Oh, sure.
Greetings and welcome, friends. Today we're talking about solving systems. All right, systems, the same things we'd seen prior when we were solving using substitution or elimination and all of those techniques. But today we're going to solve systems using matrices and specifically their inverses. But before we get into that, I want to talk a little bit about matrix algebra here. And talk about our situation. It turns out when I have a system, I'm going to represent it with a matrix equation. A times x equals b. These are all capital letters, by the way, representing individual matrices. Now, we know that, yeah, we can multiply matrices and this and that, all right? So I'll have a matrix of known values. I'll have another matrix of known values over here. And then this matrix X is actually going to be the matrix containing my variables. All right, so that's the thing that I'm trying to solve for.
So what is A and B again?
Two matrices. We'll explain more about them later. But if I was trying to solve this equation of matrices, right, normally if you were solving like a regular old equation, right, if I had the equation 2x equals 8, what would you have done to both sides to solve that?
Divide by 2.
Divide both sides by 2, right? And that would have gotten x by itself, and I would have gotten x equals 4. All right, so that's kind of our little recall over here. However, the problem with matrices is, you might realize and remember, that there's no such thing as dividing in matrices. So I can't divide both sides by matrix A. I can, however, if matrix A has an inverse, I could multiply both sides by its inverse. All right, so I'm going to, actually I'll rewrite this just to, for clarity's sake. So Ax equals, I'll leave a little space here. B, if I multiply both sides by A inverse, that's going to help us get rid of matrix A. All right. And notice that I'm multiplying on the left on both sides because matrices and multiplication are not commutative. All right, so this is what I got to do. So A inverse times A. What happens when I multiply a matrix by its inverse? I get what?
0.
No, the identity matrix. So I'll call that matrix I. Right, so matrix I is the identity. So remember, little side note maybe I'll point out is that if this was if this was a 2 by 2 matrix, I sub 2, remember, was 1 0 0 1 was the identity matrix. And what happens when I multiply the identity by any other matrix of the same size? What should I times x equal? What's the identity for any operation do? If I have the additive identity, right, was 0, what is x plus 0 equal to?
0.
X, right? What is the multiplicative identity? That was 1. If I have 1 times x, what do I get? X, all right? So the idea behind an identity is that when combined with an operation, it doesn't change what I was operating it to, all right? So the identity multiplied by matrix X, in fact, is just going to equal matrix X. And I get matrix X is equal to A inverse B.
So we just got rid of the I. Why again?
Because multiplying the identity by X is just going to give me X. Just like 1 times X is X.
Can you write that down?
We did yesterday. So the identity multiplied by any matrix is going to give me just that matrix. It leaves it unchanged.
That would be the answer.
Well, that gives me X. And X being the matrix that contains my unknowns, I've just found a solution for A inverse B. All right, and this is going to be our little formula that when I set this up in a moment, we'll be able to solve a system using inverse matrices is going to be the idea, and I'll explain in further detail where A and B come from. So let's put this to work. So remember, X is equal to A inverse B. That's the big idea. Big idea. Technically, you could do all of this matrix work every time, but it's pretty much exactly the same, so you can almost view this as a formula if you'd like. So here's our example. Here's our system. All right, not unlike systems we've dealt with before. I've got two variables and two equations in this case. So,
Wait, don't start yet.
Yep.
The stuff that we were doing last time was kind of confusing.
yeah, we know other ways of solving this system. I could solve by substitution by solving for x and substituting the revised equation, blah, blah, blah. I could solve by elimination. I could multiply the second equation by -4, or the top equation by 6, and the bottom equation by 2, and eliminate a variable, right? I've got those other techniques, but inverse matrices are going to be powerful because you might recall that substitution and elimination on a 3x3 was not fun, never mind a 4x4, 5x5, 10x10, whatever by whatever. Where matrices and technology will be able to make that a lot easier for us. So the first thing I want to talk about is matrix A. And matrix A is going to be, in this case, a 2x2 matrix made up of the coefficients. Okay, so matrix A is going to be 4, -2, 1, and 6. And it's coming directly from the coefficients of my variables when they're set up in this way. All right, so I've got to have x, y equals constant sort of thing. Now my variables matrix, I'll call matrix capital X. And this is a little bit abstract, but it's a 2x1 matrix. And it's just going to contain x and y. So I guess I could label this as my variables matrix if I wanted. All right, is what that's composed of. Now, lastly, I'll have matrix B, which is another 2x1 matrix. Intriguing. And that is going to be made up of the constants, or the right-hand side. Is where that comes from. And now I'm claiming that A times X equals B. And I don't think that's immediately intuitive. All right. I'm going to do a little check to verify that. Although you don't have to normally write this part down in order to do these problems. I'm just going to show it to you once so you believe that it's true. Check,
This on the quiz?
is A times X equals B. All right. So, so matrix A, right, 4, -2, 1, 6. If I multiply this by matrix X, X and Y, this I'm saying is going to equal 16, 17. So first of all, let's analyze the sizes of these matrices, these dimensions. Matrix A is what size?
2x2.
Yep. Matrix X is 2x1. Can I even multiply these?
Yeah.
Yep, the inner numbers match. And it should equal a outer number 2x1. And is that the size of this? Yeah. Okay, so that seems to make sense. So let's actually look at what multiplying this would be. So I'm expecting it to be a 2x1. My first row, first column element would come as a result of multiplying the first row by the first column. So 4 times x is 4x. -2 times y is -2y. And that would be my first column, first row element. So this is a single element, I want to point out. That's not 2 rows there. And my second row, right, first column element would come from the product of the second row and the first column. So 1 times x is x, 6 times y is 6y, and that's positive 6y.
Wait, so it would be 1 times x and then 6 times y.
Yep. And notice, now I'm saying I've got one matrix equal to another, and therefore their corresponding elements are equal, and that would tell me that 4x minus 2y equals 16, and that x plus 6y is equal to 17, which is my starting information. So do you guys agree so far in this matrix setup representing this problem?
We.
All right, cool. So this work you don't ever have to write down for these problems. We just believe it to be true. Don't write this for every problem. All right, I just wanted to convince you that this made sense, all right, why I have a coefficients matrix, a variables matrix, and a constants matrix. So now that I know what A, X, and B are, we had our little formula from earlier. What is matrix X also equal to? Well,
A inverse times B.
matrix A inverse times B. So my objective now, all I have to do is figure out, step 1, find what A inverse is. Step 2, multiply it by B, is all I'm going to have to do. All right, so let's do that. So let's see. So matrix A was, what now? Was it 4, 2, 1, 6? There was a negative in there, thanks. Thank you. So in order to find the inverse here, first thing I'm going to have to do is find the determinant. So matrix A's determinant is going to be 4 times 6, multiplying that primary diagonal, subtracting 1 times negative 2. So that's 24 plus 2, or 26. Now, the fact that that is not 0 tells me what? That it has an inverse. So that's good news for us, because if I can't find an inverse, I can't multiply that non-inverse times matrix B.
Can't do it.
And that would mean that the problem probably was a no solution or a infinitely many solution. I would have to kind of analyze it a little bit further to figure that out. So A inverse is equal to 1/26 multiplied by the matrix. And now it's the same as matrix A, except I switch the primary diagonal, so it's 6 and 4 is the primary now. And I opposite the secondary diagonal, so -1 and +2. Now I could distribute that if I want, but I don't want to do that. Why don't I want to do that? Because I'm going to want to multiply A inverse times B in a second, and I don't want to deal with all these fractions. So I'm going to leave this 1/26 to the very end, I hope. It's my goal. All right, so that's A inverse. I've got that done. Good. Part 2, I'm claiming, all right, according to our little formula, that X is equal to A inverse B. All right, so let's actually do this part. So that means matrix X is equal to this A inverse, 1/26 times 6 to -1, 4, multiplied by matrix B, which is the 2 by 1, which was what, 16, 17 was it? If I recall correctly. So in order to multiply this out, like I said, I'm going to save this scalar until the very end. Let's multiply these matrices first. So 1/26. And 2 by 2 by 2 by 1 is going to give me a 2 by 1. Might have a little bit of work to do on it first. Let's see, so let's multiply first row by first column to get my first row, first column element. So 6 times
16.
60 plus 36 is what? 96. Plus 2 times 17 is what? 34.
Keep going.
All right.
You're welcome.
And now second row, first column.
Negative 16.
Nice, Jacob.
Thanks, thanks. 68.
Nice, Jacob.
Thanks, thanks.
Wow, 68. Man, this guy's fast.
You sure that.
Oh,
Rapido. All right, so let's.
110.
Whoa, slow down, slow down. Let's.
Sorry.
All right, so 110.
Yeah.
I might disagree with that one.
Oh my god.
You lost.
all of our flaws.
130.
And
And negative 16 plus 68.
Okay, let me do this.
Is that 50?
No, it would be 52.
Is it? I think so.
Yep.
And now I'm just going to multiply those by 1/26, which is the same as dividing by 26. And I get the matrix 5, and 52 divided by 26 is 2. So that's matrix X, capital X.
So you just put 26 in
Yeah, you divide.
Yeah, I just multiply, yeah.
Okay. Easy enough for me.
So if matrix X is 5, 2, what does little x equal? And little y equal? Little x is the 5, little y is the 2, and if you wanted, you could write that as an ordered pair as well.
Little guy, huh?
All right. So yeah, this seems like, I mean, if I was doing this by hand, this is probably more work than solving by substitution or elimination at this point for a 2 by 2, but this concept applies to much larger problems,
Like what?
like 3 by 3s and 4 by 4s and n by n's.
But I thought we were never going to use a 3 by 3 or a 4 by 4.
I'm not going to make you derive the inverse of a 3 by 3 by hand, but we'll do that with technology right now. Tecnología.
Do you need this for homework too?
Yeah, absolutely. Don't worry about it. It's good. It's good. So here we go. Example. Last example for today. Just 2 examples today. Isn't that nice? Yeah, because you guys could learn this so quick. It's good stuff.
Quicker than, what is it? Quicker than money? That got it?
Quicker than molasses wrapped in honey. Maybe.
Yeah.
I don't know if that even makes sense.
Sounds good.
All right, solve using inverse matrices. So, all right, so here, notice I've got all my variables on the left, kind of in the same order, my constants on the right. So matrix A, here, no more noise pollution now, friends. Come on. Let's focus here. Matrix A is going to be my coefficients matrix. What are the coefficients of my first row?
I don't know if they wrote them down yet.
All right, yeah, you guys are still writing down that problem. We'll just hang out for a little bit. So, while you guys are writing, I'll just talk. So, remember, solving this system would have taken up like a full page of work by hand on previous methods, right? I could have, eliminated the z's twice and then had a system of 2 and then solved that using elimination or substitution, all sorts of different things like that. Wouldn't have been fun. Or I think you guys probably agree. It wasn't amazing. I mean, it was a little puzzle solving. But let's see. Let's do this using matrices. So matrix A is composed of the coefficients of this. So it's a 3 by 3 because I have 3 equations, 3 variables. What are the coefficients of my first row? 1, 1, negative 1. Yep. What about the second row here? Yep. 1, 1, 1.
Why no?
It's just the coefficients of x, y, z. And then the third row,
Oh, 3, negative 2, 1.
negative 1, yep. So matrix X, capital X there, will be 3 by 1 now. X, Y, Z, or Z. And matrix B is a 3 by 1, and it's just my constants, negative 1, 3, negative 4. So, all right, so we got that concept. Now, what is matrix X going to equal?
A inverse B.
A inverse B. Exactly. So the first thing I got to figure out is what is A inverse? All right. So if I found this by hand, that'd be great, and then I'd be able to multiply by B. But I'm going to show you calculadora.
Wow.
Oh no, it's got the blurries, friends. Don't worry about it. Just follow along. Follow along. Here we go. Can it focus? There we are. So, all right. So here's my calculator. All right, we showed you guys how to do stuff with matrices before on calculator. To access the matrix menu, you hit second and matrix right there, bam. All right, and notice I get, some names of matrices, right? And what I would do is I'd go over to the edit menu. All right, edit, and I'm gonna edit matrix A, why not? You don't necessarily have to line up A with A, but we might as well. And I'm making a 3 by 3 matrix. And then I'd edit the elements. Wait a minute, does this calculator happen to have the same matrix stored in it a whole semester later? Apparently.
Oh.
So this looks like 1, 1, negative 1, 1, 1, 1, 3, negative 2, negative 1. So you could have entered those all in my case, it's already there. So good stuff. So matrix A is in there. Let me quit out of this and go back to the matrix menu. And let's edit matrix B, make sure that that's good. So go down to matrix B, bam. And it's a 3 by 1 and negative 1, 3, negative 4. That's the right-hand column, right? The constants. That's also happens to be the right stuff. All right, so I've got those in there. So I've got matrix A and B, but I'm looking for A inverse. So let me show you how to do this. So I'm on the home screen, little blinking cursor. Let me go to the matrix menu, second matrix, and I'm going to hit enter under the names column for matrix A, and I want the inverse. Now notice this right here, right? The primary source of the matrix button is to the negative 1. That's the inverse button right there. So if I hit that right there, oh what? No you didn't. That's A inverse. All I have to do is hit enter right now, and bam. I get my A inverse, and I'm going to grab a little snapshot of that real quick like so. So there's A inverse. All right. So once you have A inverse, which by the way you could probably have like 1/10 in front of the matrix, 1, 3, 2, 4, 2, negative 2, negative 5, 5, 0, if you didn't want to have those decimals, but it doesn't matter. The calculator's doing the work for us anyway. So there's A inverse. What do I want to do with A inverse? Jacob told us earlier. X is equal to A inverse times B. So let's figure that out. So on El Calculador, go back to this. Let me just hit second entry to pull that up again. So I've got A inverse, and I'm going to hit multiply, plain old multiplication, right? And I want to multiply by B, so I go back to my matrix menu and go down to B in the names, and I've got A inverse times B. What size am I expecting this matrix to be? 3 by 1. Let me hit enter, and behold! Wow. Amazing. Is it not?
Wow.
Yeah. So that means that X is equal to the matrix 0, 1, 2. Very creative numbers apparently there that I've selected for us. And that means little x, little y, and little z are?
X equals 0, y equals 1, z equals 2.
Yep. Or I could write this as a ordered triple,
0, 1, 2.
which represents a point in three-dimensional space at which all of our planes, P-L-A-N-E-S, intersect and have a common location. All right, so instead of solving this by hand, your calculator and matrix inverses were able to shorten it up for us quite a bit. So good stuff. So thanks for watching, Internet friends. Have a great day. Bye-bye.